Hello, everybody. Good morning or afternoon, depending. My name is Rodrigo. I am a double PhD student between the University of Groningen here in the Netherlands and UNAM in Mexico. And today I will tell you about our latest work in kinetic gauge friction in natural inflation, which was a collaboration between some people here in Groningen and some people in Madrid. This is the archive number in case you are interested in further details. Just let me thank the organizers for giving me the chance of participating in this event. This is the outline of my talk. I will start with some motivation, then I will introduce and present the model together with its background dynamics and the perturbations on it, which will naturally transition into the calculation of some observables, and we will end up the discussion with some conclusions and a brief outlook. In order to set up the stage, we know that inflation has become the most widely accepted mechanism for the description of the early universe, although it was first conceived as a solution to some of the lambda CDM puzzles, among others, the horizon and flatness problem. Indeed, in figure 2, we are seeing a schematic representation of the horizon problem. Later, it was realized that inflation also contained a mechanism for the seed of structure formation in our universe, thus gaining more attention. In its simplest description, inflation is modeled by the Einstein action together with the addition of the action for a scalar field. This scalar field potential has to feature a flat region where inflation can take place. In figure 1, instead, we are looking at the observational constraints coming from the Planck satellite to two of the main observables of inflation, namely the tensor to scalar ratio in the vertical axis and the primordial tilt in the horizontal axis. This picture also features some theoretical predictions of diverse models of inflation. Then let's move on to the phenomenological model building and how can we write down a model of inflation and what do we need to consider. Among the many challenges to write a successful model of inflation, we know that polynomial potentials of inflation have been ruled out by observations because they overproduce tensor fluctuations. A second challenge comes from the requirement of having this flat region of the potential, which is in general ruined by the presence of higher order operators in the Lagrangian. A possible solution to this is to consider a symmetry that will protect the potential from this higher order correction. This protection works as follows, and here I am using the shift symmetry as an example, as this is the symmetry we are focusing on in this work. The shift symmetry only allows for derivative couplings. Therefore, if one writes down higher order terms in the Lagrangian, due to power counting, these higher order terms will be immediately suppressed by a mass scale, therefore protecting the potential from these quantum corrections. The most widely spread model that features this shift symmetry is the so-called natural inflation model, which is still characterized by a minimally coupled scalar field, but now this scalar field has a sinusoidal potential. However, this model only grants enough inflation for trans-Planckian values of its decay constant f, and even in this scenario, this model has already been ruled out by observations. However, much effort has been made in order to reconcile natural inflation with sub-Planckian values of f, together with accurate observations, predictions, at the level of the CMB. In this talk, we will focus on what is known as the friction mechanisms, which will serve to reconcile natural inflation with sub-Planckian values of the decay constant. First of all, we have the gravitational friction, which is the coupling between the Einstein tensor and the kinetic sector of the scalar of the action field. This new coupling will work as a further source of friction in the axion dynamics, as can be seen from equation 3. Therefore, as the axion rolls down its potential, these terms will kick in, thus slowing its roll down the potential, thus allowing for the consideration of sub-Planckian values of the decay constant. Another option is what we call the gauge field dissipation. This is typically encountered in models like chromonatural inflation. Chromonatural inflation model, the chromonatural inflation model is characterized by the presence not only of the axion field, but also the presence of non-Abelian gauge fields and the interaction between the non-Abelian gauge fields and the axion field via the Chern-Simons interaction term, which is this last term in the action. Indeed, this term, when looking at the equation of motion for the axion, will serve as a source term. Therefore, as the axion rolls down its potential, it will shed energy into the gauge sector, thus losing energy itself, allowing for sub-Planckian values of the decay constant. In this spirit, we then propose that a model in which the role of friction is played by the gauge fields themselves and not by gravity. Therefore, we propose a model in which we encounter couplings at the level of the kinetic terms for both the scalar or the axion and the gauge fields. And we will also consider the Chern-Simons interaction. As you can see from power counting, these new terms, what we call the kinetic gauge friction terms, are operators of dimension 8, which make the couplings lambda 1 and lambda 2 to have units of energy to the minus 4. In the paper and in this presentation, we will stick to the case of lambda 2 equals lambda 1 halves for simplicity, and in the background, we will ask for analytical control, therefore requiring that the Chern-Simons vanish. And later we will numerically solve the model and compare it with the case of vanishing Chern-Simons term and non-vanishing Chern-Simons term. But before moving to this, let me just give a brief UV motivation for the consideration of such couplings. These motivations come from the consideration of the dBi action, which expanded at alpha prime squared order, features the kinetic terms for both the scalar field and the gauge fields. However, if we carry on this expansion up to alpha prime fourth order, we encounter our new kinetic gauge friction terms, but we also encounter higher order corrections to the kinetic term of the scalar and to the kinetic term of the gauge fields. And indeed, these last two are featured in what is called as the gaugeflation term, which is characterized by the F fourth term, and the K-inflation model of inflation, which is characterized by the higher order correction to the scalar kinetic term. Okay, then let's now move on to the background dynamics of the model. Here I am presenting both the Friedmann equation and the axion equation of motion, where we have used this decomposition of the gauge field due to the fact that as we are considering non-Abelian gauge fields, these gauge fields have a non-zero BEV represented here by Q. Note that this is only possible if we are considering non-Abelian gauge fields. In the left figure, we are plotting the relative magnitude of the main contributions to friction. In red, you see the relative magnitude of the Hubble friction, and in black, the relative magnitude of the newly introduced friction proportional to lambda 1. Here we see that we are working in a regime where the dominant source of friction is due to our new coupling, the kinetic gauge friction couplings, and not due to the Hubble friction. On the right-hand side, instead, we are looking at the relative magnitude of the main contributions to the Friedmann equation. And we immediately see that the Friedmann equation is still potential dominated. This means that inflation is still driven by the potential of the axion field. In the background dynamics, one can also calculate the number of EFOLs, solving this integral here in equation 11, and we can further calculate the maximum amount of EFOLs one can have in this model that ends up being a combination of the model parameters. And indeed, one can plot this combination, leaving f and lambda 1 to run freely, and we can immediately see that the requirement of having at least 6 defaults of inflation, denoted here by the red line in this curve, is easily achieved for sub-Planckian values of both f and lambda 1, which is already solving one of the challenges of natural inflation. Now, let's talk about the perturbations of this model, starting with the sound speed and some instabilities. If one considers the action for the model, one can expand this action in perturbations up to second order, therefore obtaining an action for the perturbations alone, which can be then varied in order to get the equations of motion of the perturbations. However, just from the action, one can read off the coefficient of the term proportional to the gradients, which end up being the sound speed, in this case for the gauge tensor modes. We can approximate analytically this sound speed to be equation 13, where we see that the role of the Chern-Simons term is crucial at the level of the perturbations, because if we set lambda equals to 0, the second term vanishes, and thus we are left with a negative sound speed squared, as we can see in the plot here, thus signaling an instability of the model. Therefore, the Chern-Simons term plays a crucial role at the level of the perturbations, avoiding the negative sound speed squared. However, one can immediately say, ask the question, how much lambda is enough for us to have a positive sound speed squared? And indeed, one can easily verify that lambda has to be higher than this combination of parameters and background quantities here in order to enforce a positive sound speed squared, as we can see in this plot. However, in doing this work, we also imposed another restriction in both lambda and in the model dynamics. If we remember when we demonstrated the model, we showed that our model, the kinetic gauge friction model, contained both the kinetic couplings between the non-Abelian gauge fields and the axion fields, together with the Chern-Simons interaction. So there is an interplay between these two terms. If we take lambda to be too large, then the Chern-Simons interaction will dominate over the kinetic gauge friction terms, thus making the dynamics of the model to be very similar to that in chromonatural inflation. Therefore, what we do here is to ask that the contribution or the importance of lambda at the background level is subdominant compared to the contribution of the kinetic gauge friction new terms that we proposed in this work. Therefore, we have a regime for lambda in which lambda has to be big enough so that we have a positive sound speed squared, and small enough so that its contribution to the background dynamics is subleading compared to the kinetic gauge friction terms. And this is indeed what we see in these two plots. In the left-hand side, for lambda equals 30, we immediately see that the sound speed is now positive, while in the right-hand side, we are plotting the vacuum expectation value for the gauge field for different scenarios. First, numerically, for lambda equals 30 in black, and numerically in the case of vanishing lambda, and we immediately see that the two of them are in very good agreement. Therefore, this means that at the level of the background, the case for lambda equals 0 is well enough so that it captures the same dynamics or very close dynamics as the case of lambda equals 30. And we are even comparing our analytical approximation here in blue, and we also see that it's in very good agreement. So to recap, we ask lambda to be large enough so that CS squared is positive here in the left plot, but at the same time, we are requiring that lambda is small enough so that the background level is well described by lambda equals 0. which is the thing we see in the right plot. Now, let's briefly talk about the tensor perturbations. There are two sources of tensor perturbations in the model, namely the metric and the gauge fields. Due to the Chern-Simons terms appearing in the model, we have that the model is parity odd, and this means that one of the two chiralities of the gauge fields will be enhanced, thus leading to an enhancement in one of the two chiralities of the metric, as we can see in this plot. The red chirality of the gauge field is enhanced, and it enhances the orange chirality in the metric, while the other two remain at its vacuum. And finally, the scalar perturbations ended up being very different to the tensor ones because we cannot choose the Bunch-Davies vacuum as its initial condition. Therefore, we had to employ the Gronskian prescription in order to find a solution in the infinite past of the scalar modes. And here we are plotting the main contributions to the curvature perturbation, and we see that the main contribution to this perturbation is due to the axion. Therefore, we can safely approximate the true curvature perturbation as being that of single field inflation. Finally, let me just say a few words on how we choose the parameters of the models, and let me just finish with the observables that we encounter. We stick to the weakly coupled regime of the gauge fields. This means to consider G to be less than 1. As we mentioned in the beginning, we are trying to reconcile natural inflation with sub-Planckian values of F, the decay constant, so we choose F to be sub-Planckian. We choose mu, which is the scale of the potential, such that it respects the bounds on the tensor to scalar ratio. We consider the value of lambda 1, which is compatible of the requirement to have at least 60 folds of inflation. And finally, we consider lambda such that it grants a positive sound speed squared, but small enough so that the background dynamics are well approximated by the lambda equals 0 case. Therefore, we choose this set of fiducial parameters for which we find this set of observables which are in agreement with the latest CMB observations. And finally, let me just conclude by saying that this work should be regarded as a proof of concept that the kinetic gauge friction terms allow for both the consideration of a sub-Planckian decay constant while granting observations that are in agreement with the CMB measurements, observables that are in agreement with the CMB measurements, sorry. And another important conclusion is that the chiral gravitational wave spectrum is inherited from the Chern-Simons coupling. And a brief outlook, as I mentioned just now, we only explored a single point in the parameter space. Therefore, a full exploration of the parameter space is needed in order for the model to be robust. And in this work, we didn't study the back reaction of the gauge fields in the background dynamics, which have been shown to be an important matter when considering gauge fields. So therefore, this can also be an avenue of further research. And with this, I finish, and I thank you all for your attention, and that's it. Thank you very much.